So I think we are ready to get started. I hope you all had a good break. Once again, thank you everyone for all of your attention so far in this graph representation learning tutorial. As already mentioned, unfortunately, because of Gabor catching COVID, you're going to be stuck with me for 1 more hour. I hope I've so far given you good reason to at least tolerate me for 1 more hour, but I promise you this last hour is probably going to be where some of the potentially fun stuff is going to happen. So we will talk about, now that we've introduced graph neural networks from first principles and using the concept of how do you even apply them when there's no graph, we related them to some of the most popular models there are, such as transformers and even models like deep sets. We are now going to address some fundamental questions about these models, like where did they come from? How powerful are they? Can we build models that are even more powerful? And then towards the end, I think you'll have a choice. Like you can decide, you know, red pill versus blue pill. Would you prefer to read more, to find out more about the geometric origin of these models, or you will have the opportunity to listen to me rant for 20 minutes about some of my experiences in this area and how to best approach it. You can decide which of those two is more valuable. I'll leave it up to you. But for now, we will start and kind of conclude what was supposed to be the original part of the tutorial, but because I knew I had an extra hour, I slowed down a little bit to make it more clear. We will talk about the expressive power of graph neural networks, and we will study this through the Weisfeiler-Lehman hierarchy and beyond. So I'm going to remind you of a slide I made many minutes ago, where I said that when we introduced the deep sets model, I was able to tell you there are rigorous proofs that say that no matter what well-behaved set function you give me, I must be able to express it as a deep sets model. So it's universal for modeling data on sets. Now we can ask ourselves, the GNN we derived, the one that passes messages over one-hop neighbors and so on with message passing, is it equally general? Can we take any permutation equivariant function over graphs and represent it in one of the 3 flavors that I discussed? I hope many of you have some opinions about this. I would expect most of you probably have a negative answer in mind, that maybe this cannot be done. Well, let's talk about it. We will now take a deep dive into one of the most coveted areas of theoretical computer science, classical algorithms and data structures. So for those of you who have a computer science background, you might have come across things like this: sorting, searching, pathfinding, data structures, and so on and so forth. Why are these quite useful? Well, for the computer scientists in the room, you will know it's the cornerstone of any course of computer science. So it kind of gives you a mathematical and computational toolkit that you can use to talk about any kind of reasoning computation there is. But it's also notoriously painful to reconcile it with the methods we use nowadays, like deep learning, because they typically tend to have diametrically opposite properties. So algorithms are really good at strong generalization. They're very interpretable, very compositional. You can take subroutines and combine them together. Whereas in deep learning, we typically have little to no interpretability, almost no extrapolation generalization, and basically there's very hard to get, if any, compositionality between these models. However, looking at algorithms will prove invaluable for our journey of learning GNNs. They'll help us understand how powerful GNNs are and help us break the limits of that power. And we'll also see how GNNs and some algorithms can be very tightly related. And even by analyzing algorithms, you can rediscover certain classes of GNNs. Needless to say, this is going to be my favorite part of the tutorial. So I hope you enjoy it. So this is the apparent divide that we're dealing with here. So we have neural networks on one side, you have algorithms on the other side. And if you look at what are the things that are good about one and good about the other and what's bad, you can find that there's a lot of compatibility between these two. The things that neural networks tend to struggle with, like having to use big data, hard to extrapolate, hard to interpret, all of those things are quite trivially satisfied by algorithms. You can even theoretically prove that they will converge in a certain amount of steps or be correct or something like that. But then again, algorithms are not robust to changing the task. So you change the task a little bit, you have to throw out your algorithm and write a new one. Whereas neural networks can work directly on raw data and generalize over noisy conditions. So we're going to be using this lens of algorithms to study how powerful are graph neural networks, okay? Because by now, I hope I convinced you that graph neural networks are a powerful tool for processing real-world graph data, and they can solve many of these problems to a really satisfactory level. They still won't solve any task specified on a graph accurately. And this is very important to note. You know, many interesting tasks on a graph, somebody mentioned combinatorial optimization. Many of those interesting tasks are NP complete. And what we've done here is still polynomial time. So unless you're about to win $1 million and tell me that P and NP are the same, very likely there exist some problems that graph neural networks cannot solve. So how can we reason about what are the things they can do and they cannot do? Well, one canonical example that we like to use in graph representation learning to measure this power is the task of deciding graph isomorphism. What does it mean in the context of GNNs? We ask ourselves, can this GNN distinguish two non-isomorphic graphs? Like, can I attach different graph representations, these latents, to the two graphs that are not the same? If you cannot give them different embeddings, any task that has to discriminate them is hopeless, right? Because you must classify them the same way. So in a way, this idea of telling us which graphs we can distinguish in this lens of isomorphism is the most general task possible. Can I even tell them apart, let alone put them in different classes? Okay, so we're going to try to formalize this, and it turns out to formalize this, we'll study a very popular algorithm for approximately deciding graph isomorphism, and that is the Weisfeiler-Lehman test, or 1WL for short. It is, by this point, a very old algorithm invented by these two Soviet mathematicians, Andrei Lehman and Boris Weisfeiler, and it's a very simple but super powerful way of telling graphs apart. You just compute random hashes in every node, you pass them along the edges, and you sum them up. And you iterate until these hashes are semantically different. Whenever you stop, you take the hashes of the two graphs you're looking at, and if their hash histograms are the same, you say they're possibly isomorphic. Otherwise, you stop and say they're not isomorphic. And this explanation might not be completely clear, so I'm going to try to make it very clear. We're going to run the Weisfeiler-Lehman test together. And I said we're going to deal with hashes, but actually you can deal with hashes as colors, because that just means you're counting different possible hashes that you might have. And what does random hashes of sums mean? We're just going to track all the possible color neighborhoods and assign different colors to different situations. And we stop when the color distribution stops changing. Okay, so we have this nice graph here. We're going to start with every node has the same color. And after one step of the Weisfeiler-Lehman algorithm, this is what we get. We have two different situations. We have a blue node with two blue neighbors, which we color a certain color, like green. And we have a blue node with three blue neighbors, which we will color a different way, yellow. Okay, so hopefully now it sort of makes sense what this algorithm is trying to do. Can someone tell me what we should expect to see when we run it one more step? How many colors? 3 colors. Okay, so who gets the new color? Yeah, the node at the top would have to get a new color, right? Because it introduces a new situation, right? So now we have 3 situations. A green node with a yellow and green neighbor, that gets 1 color, like gray. A yellow node with 1 yellow and 2 green neighbors, that gets 1 color, red. And this top node is a new situation, a green node with 2 yellow neighbors that gets a new color, purple. And I hope you can convince yourselves that if you do this one more time, nothing changes. So you stop and you output a histogram. 1, 2, 3. Yeah. Now, if I run the same procedure on a graph which looks very different, but is actually exactly the same graph. In fact, if you look at this carefully, you'll see these two are exactly the same. I just chose to present this graph to you slightly differently. You'll end up with exactly the same histogram. So the Weisfeiler test will completely correctly say these two graphs are possibly isomorphic. Okay. And, you know, this feels a lot like a graph neural network, right? Because you're passing neighborhood information along the edges of the graph and using that to update your representations. So people were able to spot the connection to this test very early. And as early as the GCN paper, you have the statement of the Weisfeiler algorithm inside that paper. So people have realized this is very powerful. And it also, by the way, explains, because these are random hashes, right? Just random colors, it also explains why random GNNs, the ones you just initialize and don't even train, can be really powerful to distinguish your neighbors. Like that's why SGC works very well, right? You just aggregate, 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 and then you classify at the end. That works really well, okay? However, even though the Weisfeiler test is super, super powerful for telling apart most real-world graphs, it does fail in some painfully simple scenarios. This is one. The Weisfeiler-Lehman test cannot tell apart a 6 cycle from 2 triangles. That's pretty important, right? Because many interesting problems on a graph rely on you being able to recognize these kinds of substructures. Why does the Weisfeiler test fail here? Because from its perspective, every node looks exactly the same, right? In these two diagrams. There's no way of telling them apart. Okay. So it might shock you to find out that when our features are discrete, you can prove that a GNN can never be more powerful than this test. Okay. So it was certainly quite shocking to me when I first found out about it. So GNNs can never be more powerful than this one Weisfeiler-Lehman test at distinguishing graph structures. And what's worse is that if you want a GNN that performs exactly as powerful as one Weisfeiler test, you need to be careful on the hyperparameters of the model. Specifically, if you want to get maximal power, you need to have an injective permutation invariant aggregator. One example of this in the discrete feature case is sum. So if I have a neighborhood like this of blue and red neighbors, summing them up like they're one hot features will capture the multiplicities of every single one of them. So I've captured the whole neighborhood. The moment I take an average, I'm already just capturing the distribution, like what's the ratio of blues to reds. And if I take something like max, that's even worse. I'm reducing all the multiplicities in this set. So I hope this gives you kind of a visual representation of how, in this case, summation captures more information about the neighborhood than the other ones, okay? And in fact, the way in which you prove this is very similar to the proof you do to show that deep sets are universal. The main difference is that now inputs are no longer sets, they're multi-sets. So a feature can repeat itself. So you must be careful about which aggregator to use. Yes? The fact that you're storing representations in nodes. The K Weisfeiler test will store representations in pairs or triplets or something like that. We'll get to that as well in a few steps. Yes? The neighborhood itself is a multiset. That's, I guess, the point, right? In this particular case, the features are discrete, so you're very often going to be in the case where the same feature appears twice, and then therefore you'll need a multiset. In real world scenarios, and we'll touch upon that some slides later, actually features might be continuous, and maybe this situation doesn't happen that often. But at least when the features are discrete, you can prove that sum is the one optimal way to capture the diversity in that set. Okay. And actually, the authors of the paper that showed this built then a model called the graph isomorphism network, kind of to align with that algorithm, or GIN for short. And it's like a simple graph neural network that follows this principle of you should use the sum aggregation. And it's as simple as possible, but satisfies this constraint of being as powerful as the Weisfeiler test. You can see clearly it uses a sum aggregation over all of the neighbors. And it has a special way in which it weighs its skip connection so that it tells apart the central node from all the other nodes. Specifically, it has to add this epsilon to make it theoretically distinguishable. In the original paper, epsilon is an irrational number because all of these guys are countable features, and this one will then have to be somehow non-countable to tell it apart. In reality, computers cannot represent irrational numbers, so this epsilon is just a learnable weight. But that's the general idea. And you make this phi a universal approximator, so it must be at least a 2-layer neural network to model any kind of set aggregation. Okay, so this is interesting. I've just told you something seemingly quite damning, which is I cannot use a GNN to tell these two things apart. So that sounds a bit damning, but you know, in reality, it's not a bottleneck we cannot cross. We can actually make graph neural networks stronger by looking at what are the cases where they fail and then fixing them up somehow. Needless to say, it's a super active area. There's many open problems and many papers published on a daily basis trying to build stronger graph neural networks like this. But the general idea is always the same. We know that they cannot compute something, give them that information that they cannot compute, and then they'll be able to do it. That's the general idea. So let's test the temperature in the room. Let's see if we're able to derive a 2021 research paper all by ourselves in this area. As we said, a simple GNN cannot tell apart these two different graphs. And that's because if you look at the receptive field of every single node, so these are like all the neighbors that you see, they all structurally and feature-wise look exactly the same. So there's no way for a graph neural network to tell them apart. So can you give me a very simple fix I can do to this graph's inputs to fix this problem? Any ideas? Yes?
It add its own unique representation of itself.
There we go. You can actually do something even simpler than that, which kind of amounts to the same thing, which is put a random number in every single one of those nodes. And what can we do now when there's a random number in every single node? Well, now a node can see itself a certain number of hops away, and therefore you know you've closed a certain kind of a cycle, right? Yeah. And this basically allows you, for some notion of reasoning about it, you can tell that you can see yourself k hops away, right? And this now allows you to tell apart certain kinds of cycles. And this idea, put a random feature on the nodes and then mathematically prove why this is good, but this is generally the intuition, how you can prove it mathematically, and then do a few simple empirical experiments to demonstrate that it works, is sufficient to publish a top-tier paper in this area in the year of 2021. So this is just to say how accessible this area is if you want to potentially attack it. Like find a failure case that GNNs cannot solve, invent something potentially as simple as put a random identifier in every node, prove that it works. You have a research paper. Okay, this is just to make it clear what the barrier of entry is to this field right now. And of course, it's just one instance of a more wider family of methods that put features on the nodes to give them powers they might not have. In this RPGNN, actually, we do exactly what you suggested. We put a one hot identifier on every single node. That's it. Like with some other theoretical analysis, they basically do this in this paper. There's other positional methods like the PGNN, which allow you to do some more interesting graph structure analysis to compute what's the node's position inside the graph and put that as extra features. Or even you could literally, if you know some subgraphs are interesting, you could literally count them. Like, is this node in this kind of subgraph, like a K-clique or something, and put that as an extra positional feature. This is very common in computational chemistry, by the way. We know that chemical rings are a very common driver of chemical function, but we know graph nets are not easily going to detect rings. So why not just pre-compute? So pre-compute which atoms are in a ring and put that as an extra feature. That works really well, right? So all we're really doing here is we're doing manually some computation that the GraphNet cannot do or cannot do easily, and we give the GraphNet that immediately as a feature, so it can use it. Yeah. And whenever you fix a failure case of the Weisfeiler test like this generally gives you something of an augmented message passing flavor. Yeah. And you can broadly categorize them into three general directions. I said there's a lot of efforts going on here, but one general direction is, as we just discussed, to put some features in the nodes or edges to tell apart the different structures. You could also modify the message passing rule to be more mindful of the graph structure. The directional graph network is a really good example of this. Or you could also modify the graph structure you're doing message passing over. One standard example is this 1, 2, 3 GNN, which, according to the question Joao was asking, represents features in tuples of nodes rather than just a single node. And that way allows you to model more complicated triplet structures in the graph, for example. And this modification of graph structure, by the way, further subdivides into rewiring the graph, aggregating over subgraphs, or even inventing new nodes that correspond to substructures you care about, and then making that node responsible for the whole substructure. And that way you have a message passing that's mindful of the interesting things inside the graph. Also very common in computational chemistry. Now, one thing that's very important, because I hope I've inspired at least some of you to take a closer look at this field, is that if you actually start to look up methods that improve on this limitation, there's a high chance you'll come across certain terms like higher order GNNs or beyond message passing. I'm not using those terms. I use the term augmented message passing. And there's a good reason why I did that. Like when I first gave my master's course here at Cambridge, I proposed that, using the term beyond message passing, I tried to use it in a lecture. It just sounded a bit weird because when you say beyond message passing, it sounds like you shouldn't use message passing at all to implement this thing. But in reality, very often you are using message passing. It's just over a slightly different graph. Or you use something which is maybe reasoned about as a tensor product, but even that is a case of message passing, perhaps trivial. But basically, what I've convinced myself after a lot of debate with many other experts, both internally and externally, is that it's not easy. It's likely impossible to truly make a GNN that you cannot express using message passing, right? And actually, many of these stronger GNNs with substructure message passing, you can most easily implement them as message passing, just over a slightly different graph. So the trick is really to modify the graph you're doing message passing over. So I conclude that using the term beyond message passing is likely to be imprecise at best, and it might be harmful at worst because it might get you to think you need to implement it in a way you're not supposed to. So it started by, this slide I showed you earlier on how I believe you could extend this to hypergraphs and beyond, but probably you can use exactly the same framework. And some of my teaching assistants took note of this slide and said, maybe I should change it. And it launched a 35 reply discussion where the original poster basically said they opened the Pandora's box. So it was a very interesting discussion, but it eventually led to me actually writing an opinionated position paper on the top. Say that basically with simple pairwise message passing, you can do everything. So with the simple one hop GNN, everything works. You just need to redefine what are your nodes and what does one hop mean. But after you do that, it all boils down to this. And the paper did spark quite a lot of interesting debate, and it was presented at a spotlight at a workshop some time ago. It's very short, 4 pages and basically no maths. So if you're interested in some more opinions on this and some more literature survey in the area, I'd invite you to check it out. It's publicly available in the archive. And the second term, so not just beyond message passing, but there's a second term known as higher order GNNs, which actually relates to this idea of one Weisfeiler-Lehman. It can be generalized to a K Weisfeiler-Lehman test, where you keep track not just of the hash inside a node, but hash inside collections of nodes, like K tuples. So pairs of nodes or triplets of nodes or something like that. And usually when you say higher order GNN, it explicitly relates to a GNN that's as strong as the K Weisfeiler test. But the reason why I don't prefer to use this term for all of these approaches is because not all expressive GNNs are best talked about with respect to this Weisfeiler test. If you remember, the main premise of the Weisfeiler test was to decide isomorphism over graphs that have discrete features, okay? But what if the features are not discrete? It's very common in the real world that the features might be continuous. And even like the latent states, like imagine if you have a graph of images, for example, you might first apply a convnet to compute features of every image and then do a graphnet to combine different images together. The features you get are also going to be continuous vectors. Well, up to what computers can represent, but it's best to think about them as continuous because all the universal approximation proofs come from a continuous assumption. So what happens when features are continuous? The original authors of the graph isomorphism network said, we leave the continuous case to future work. And I think they even hinted that it might be a simple affair to kind of get it to behave. Well, actually, it turns out it's not a simple affair. And when you put continuous features in the nodes, all of those previous proofs that you should use the sum aggregation fall apart. And here's a few concrete examples to hopefully convince you of this. So here's a few pairs of neighborhoods where I put continuous features in the nodes, so not discrete, but continuous. And now I have these different aggregation functions like mean, minimum, maximum, standard deviation. And I've highlighted the ones that fail. Specifically, I'd like you to focus on this neighborhood over here. If you look at it, so 0242 and 0044, clearly they're different. So they should be non-isomorphic, but averaging or summing doesn't tell them apart. Minimum doesn't tell them apart, maximum doesn't tell them apart. In fact, you need standard deviation to tell them apart, okay? And for some others, standard deviation is not a good idea. So there seems to be much more tricky in this particular continuous setting to talk about what's the best aggregation function. And, we set out to investigate this together with some undergraduate students here at Cambridge, Gabriele and Luca. And we basically discovered that there is no winner aggregator. Like in our paper, which came as a result of this discussion, we were able to prove that if you have n neighbors and their set is the set of real numbers, you need at least n aggregators to tell apart non-isomorphic neighborhoods. Okay, so you need one aggregator per neighbor. And for the mathematicians in the audience, you might find it very interesting to read the mathematical proof of why this is true, because we prove it using the Borsuk-Ulam theorem, which is completely kind of wacky that we're able to apply it in this particular setting. And if you like watching visual mathematics, and like myself, you like 3 Blue 1 Brown, who, if you haven't explored him before, I highly recommend. He's an amazing math communicator on YouTube. He actually made a really long video just on the Borsuk-Ulam theorem, which I highly recommend. It's a nice, like, geometric view of this fascinating mathematical fact. So, like, I just think that the math behind this is really cool. It's not necessary to understand it to proceed further in our discussion, but yeah. So we've been able to prove that if you have n neighbors, to be able to tell them apart with real valued features, you need at least 10 aggregators. But that still doesn't tell you what are those n aggregators. So how can I, even though I know it's very expensive, how can I create n aggregation functions that work? Well, we prove in our paper that one collection of functions that works are the nth order moments of the neighborhood. So what this means is you take the nth power of the expected value of how far away you are from the mean, and then you take the nth square root. As you iterate n, you go from mean to standard deviation to skew to kurtosis and so on and so forth. You can even cover things like max and min because they together give you an estimate for m infinity, right? It's the biggest distance in your neighborhood. So this also explains why max and min are quite powerful. And one thing that's quite important is that we prove that this is one combination that works. It is not always the optimal choice, depending on what task you're solving and what kind of numerical stability you want. There might be different combinations of aggregators that work better for your case. And in fact, the directional graph network paper that I mentioned some slides ago is one example of tuning these n aggregators to be more mindful of the geometry of the graph. Okay. And one thing that's also quite important when considering using this idea is that when n is bigger than 2, so when you go into skew and kurtosis territory, this thing is getting a bit numerically unstable. Like you have to take nth powers followed by nth square roots. Like you can imagine, this is potentially a bit tricky. So what do we do in our paper? Because we don't want to just give you a bunch of theory. We want to also give you something you can practically use. We propose what we call the principal neighborhood aggregation layer, or PNA, which is a empirically interesting combination of aggregators that should be numerically stable. So we take those moments which we believe are stable enough. So the mean, the standard deviation, which is order 1 and order 2. And we also put max and min because order infinity remarkably gives you another kind of stability. And those 4 aggregators combined together with some scaling functions like identity, so multiply by 1, degree scalar, multiplied by the degree of the node. This is very useful because when you multiply the degree with mean, you get sum. And we know sum is potentially very useful. And also the logarithm of the degree, so you can put more emphasis on the influencers in your network rather than other nodes, right? So combine these 3 multiplying factors with 4 different aggregation functions, you get 12 different aggregation functions. And that's exactly what we do. We take these 12 aggregation functions, we apply all of them in parallel, and we concatenate the results to get our final representation. That's it. So stitch this into your favorite graph neural network of choice, and you're all set. What we found empirically is that in almost all cases, this outperforms all basic choices of the aggregator. And at worst, it matches the best performing one. So we also saw this in our Google Maps paper, for example, where a very complicated combination of deviation aggregators actually perform the best for predicting travel times in Google Maps. And that's actually the last slide of the main part of this tutorial. I think it's a good place to pause and ask if you have some questions. And afterwards, I'll maybe take 5 minutes if there are any questions. And then I'll have a show of hands to decide what do we do with the last half hour. As I said, there are 2 possible options. We can either talk more about the geometric origin of all of these models and talk about how to deal with more geometric inputs, or we can do a 20-minute rant on getting into the field, some interesting advices and experiences I've had working in the field. So are there any questions at this point on everything we covered so far? Yes? Mm-hmm. No, this is one aggregator. So Mn is one particular aggregator for one choice of n, and X is the set of all of your neighbors. Yeah. So it's like you take the mean value over all of your neighbors, you measure the expected discrepancy, right, of the nth power, and then you take the nth root. So it's like mean, variance, and so on within your neighborhood. Sorry? Oh, it's empirical. So it's the nodes that you have in your neighborhoods. Yeah. Yes?
Those emphasis on having the 12 lines. Here talks about having as many as your neighborhood.
Yes.
So then this 12 is very well, or how to arrive.
Yeah, so this was basically an empirical finding which combines the moments that are numerically stable. So order 1, order 2, and order infinity. Everything else, you take third power is already, it's a bit, like we have ablation studies where we tried to add the third power as well, and it just wasn't stable. Like it didn't give us consistent improvements and it increased the variance. So that was a bit worse to work with, right? And these scalars are just there, so identities hopefully make sense. Multiplying with the degree, we just wanted to be able to recover the sum and to preserve cardinality information. And it's well known in network science that you want to kind of preserve hub and authority information in the network. So taking the logarithm of the degree was a good way to enforce that. But yeah, so that's kind of, we arrived at some empirically motivated combination that's inspired by the theory. But if you look at, say, directional graph nets, which came after this, it's a specialization looking at the Laplacian eigenvector. So it kind of, takes a step forward in deriving these aggregators. Yes? So wait, yes, actually, good question. We tested on several algorithmic problems that were fully connected graphs. So already on those, it was a degree far higher than 12. But yes, we did also test on many real world data sets, and there the degree maybe would have been actually not that big compared to 12. So yeah, maybe empirically for many networks of interest, maybe on a social network, it wouldn't be a good idea, but on chemistry, maybe it's a good idea, right? Yeah. Question?
Is there any difference between like the input features and the data features in terms of what application is important? Because you have the possibility to adapt or features?
That is a very good question. We haven't explored it here because, since you have the combination, it kind of lets you use whichever one you want by combining them. There's additional interesting future work where you have where people have learnable aggregation functions, where basically these n's weren't anymore discrete integers, but they became a learnable parameter, right? So you could kind of specialize yourself towards max or min or sum or whatever, depending on how you gradient descend through this thing. And what they found is that usually this kind of rigid combination tends to be a bit more stable just because it has a stable behavior throughout training. But they have been able to approach the performance of PNA using these kinds of things. So yeah, I think in general, you might find it interesting to try different combinations of aggregators at different points. Yeah, that's a good idea. Nobody investigated it really well so far, just to be clear. Yes? Mm-hmm. Yeah, so okay, that's a very good point. And actually, there is a related paper that does exactly this from the point of view of matrix operations. The same way you can derive that a convolution is exactly the operation that is translation equivariant. There exists a paper, it's called Invariant and Equivariant Graph Networks from Hagai Maron at NVIDIA. It basically computes the basis of 15 or 16 basis matrices that together in a linear combination specify everything which is permutation equivariant. So it is possible to do, and they definitely do it in this paper, and they can prove it's more powerful than the simple one Weisfeiler test. I would just say that there is potentially some, just because the function can express every single one, doesn't mean it's easy to learn it through gradient descent. So this kind of function kind of isolates interesting modes of behavior, if that makes sense, and kind of lets you zone in on them rather than having to discover them from data, which might be harder. So definitely, and I recommend checking that paper if you want some more insight on that. Okay, maybe one more question. Yes?
Can you extend the same model of the extra parameter like to make the model compatible for the biocompatibility state and heat exchange problem?
So, sorry, could you repeat that? What extension do you want to make?
The same model like the insertion of extra parameters.
So where do you put the parameters? It depends.
Just like you have used mu and sigma.
Uh-huh.
So can you extend this by including extra parameters like density parameter?
Okay, so basically more aggregation functions, is that what you mean? Ah, yeah, definitely. So as I said, some slides ago, I'll just refer back to it. This paper here, the DGN, has its own basis of aggregators, which actually computes the eigenflows on the graph. And looking at the eigenflows, it uses them to define custom aggregation functions. So yeah, it's definitely possible. It can give you better performance if it's better aligned with the problem that you're solving. The specific proposal we did here was just a collection of aggregators that empirically works well on most problems of interest. But you know, really, it's just one instance of a much bigger template. Yeah. Okay, so I think now, since we have about 20 minutes left, I am going to once again offer you the chance to either listen to me talk about geometric principles of these GNNs and how we can extend them to more interesting manifolds and different geometric objects, or we can talk about the 20-minute rant. So can I have a show of hands? Who wants to listen to the geometric foundations? Okay, and who wants to listen to the rant? Okay, interesting. So a month ago, I gave a talk at a summer school in Rome where I basically, asked the same question, and it was overwhelmingly in support of the rant. It seems like the community at Cambridge prefers to hear the geometric principles. So that's nice. So let me see. I just need to find it. So we need to find. So there we go. Okay, so I'm going to need to just take a moment to change the screen that I'm sharing at Zoom. Yeah. Okay. So I'm just gonna use slideshow. Wonderful. So this is, as you might tell from the title, it's an extract of one of the lectures I give for our master course on GNNs. And actually, I give it together with Pietro, who is another lecturer here at the department. And for those of you who are potentially about to become master students, we hope you take our course. We hope you find it interesting because we get 12 hours to talk to you about this stuff as opposed to 2 or 3 hours. So I want to tell you a little bit about the geometric motivation behind all these models. And to do that, I'm going to take you back in time, way back in time to the days of this guy, Euclid, who, as you might know, is the father of Euclidean geometry, which basically for many, many centuries was the way to do geometry. It's fundamentally motivating how different objects position themselves in the plane, right? Well, many mathematicians believed very strongly that this was the way to do geometry, and they often tried to prove that Euclid's postulates must be the way they are by assuming one of them, the parallel postulate, was false, that you couldn't make 2 or more parallel lines to a particular line, and trying to derive a contradiction. But what actually happened is they did not derive a contradiction. They ended up deriving completely new sets of self-sustaining pieces of mathematics. And the earliest examples of this are Lobachevsky and Bolyai. So around the early 1800s, they have been able to take these ideas and discover what is now known as hyperbolic geometry, where you actually can draw more than one parallel line to a given line, right? And actually, Bolyai, when he first discovered this, is famously noted in a letter to his father that he has discovered such wonderful things that he was amazed. Out of nothing, he has created a strange new universe. So it was truly fascinating at the time to see, after so many centuries of Euclid's monopoly, that actually there was a different way to study geometric objects. And this then only continued through the work of, for example, Riemann, who formulated many of the interesting elliptical geometries on the surface of a sphere, for example. And, the 1800s were therefore a very exciting time to study geometry. And one big question that was arising, because every one of these geometries had its own notation, its own motivation, and so on, was what is the one true geometry? Like if I'm new and I'm coming into this field, what is the geometry I should try to study, right? And the solution to this problem came about 20 years later through the work of this German mathematician, Felix Klein, who had just been appointed to a professorship position at the Bavarian University of Erlangen in Nuremberg in Germany. And he proposed, as part of his research program, which was later on known as the Erlangen program, a blueprint to unify all of these geometries eventually, using the principles of invariance and symmetry. So basically, rather than talking about this geometry, this geometry, this geometry, specify what's the domain your data lives on, what are the symmetries of that domain, and based on that, you will just uncover all the geometric laws. And the impact of this program is hard to overstate. It had massive spillover effects into mathematics and into other areas of science. Obviously, it helped us eventually unify all of these different geometries under the same blueprint, primarily through the work of Élie Cartan in the 1920s. So it took a while before we got there, but we were able to get there using this idea. But then it also had amazing spillovers into physics. So I know there's a few physicists in the audience. You probably know about Emmy Noether. She is one of the most influential figures in physics. And she basically derived, using the same rules of the Erlangen program, that you can discover all conservation laws in physics just through the principles of symmetry. And these kinds of ideas eventually even led to the classification of elementary particles, which in physics we know as the standard model. So in a way, ideas from the Erlangen program permeated across throughout physics. And I come from theoretical computer science, and I believe there's many computer scientists in the audience also. One of the main abstract languages we use to talk about the theory of computation is category theory. And in the words of the founders of category theory, Eilenberg and MacLean, their entire field is a direct extension of Felix Klein's Erlangen program. So this very simple idea to unify different geometries through the idea of invariances and symmetries is something that permeated and went through mathematics, through physics, and through theoretical computer science, and kind of transformed all of those fields. So it's a really powerful idea. And now you might be wondering, why the hell are you telling me about all of this geometrical stuff in a tutorial on graph neural networks? Well, let's take a step back and think about what deep learning looks like around the year 2020, right? You have all these different fun models, and across all these different fun models, you have fun claims attached to them, right? Everything really is a special case of a convolution. Data lives on graphs always. You should use a graph neural network. Transformers use self-attention, and as we know, attention is all you need. LSTMs are Turing complete, so why would you ever need anything else, right? So to me, the field of deep learning around the year 2020 feels a lot like geometry in the 1800s. To a newcomer, there's a lot of these different cool models with different bombastic statements, and everybody's wondering, what is this one true architecture that I should be using, right? And you might believe that graph neural networks could be some answer to this question, because if you really squint hard enough, most of these special case models can also be seen as message passing over some kind of a graph structure. So there is a case in which GNNs could be a good template for defining this one true architecture. But to truly understand them, you need to go beyond the realm of just permutation equivariance and go beyond to different kinds of geometric objects. So then now it's our turn to study geometry and to try to unify all of this. And together, as I said, with Michael, Joan, and Taco, we are working very actively on this. Next year, there will hopefully be a book published on this topic. If you're interested, we already have a 150-page version that's public here on geometricdeeplearning.com. Okay, so geometric deep learning, GNNs beyond permutation equivariance. I'm going to do a very quick glance over the main concepts in the area, and I can jump straight into some material you haven't seen already. So in general, the reason why we want to do geometric deep learning is because learning in high dimensions is a fundamentally cursed problem, right? You've probably heard of some notion of the curse of dimensionality, where even if my target function is super simple, like one Lipschitz, I might need an exponentially increasing number of training points to fit it properly as I increase the number of dimensions. And most of deep learning takes place in a very high dimensional space. So this is a very hard problem, very cursed problem. And how do we fix it? Well, geometry to the rescue, right? We usually have some knowledge about our problem that we can inject to our architecture through inductive biases. And this makes the space of functions smaller because they must follow a mathematical property, and this makes the problem more tractable. Few popular examples: images independent of shifts, spheres independent of rotations, and as we talked about for several hours, graphs independent of isomorphism, right? And we try to formalize this in the geometric deep learning blueprint. And the general idea is you mathematically define some space omega on which your data lives, and the feature space C of that data. So say here for images, omega could be the set of all pixels in that image, and C could be three-dimensional real values, so red, green, and blue, right? And then you can define a space of all functions X that take points in the domain and give you the features, but usually features will be discrete, so we don't have to deal with functions. We can just look at them as matrices, as we did throughout this lecture with node feature matrices, right? Matrix X, which has number of rows equal to number of points on your domain, and the number of columns equal to the number of features that you're storing in each point. And I'll skip this point about Hilbert space structure. It's less important. Symmetries are more important. So a symmetry of an object is anything you do on the object that leaves it unchanged. And here's one example of this. Imagine our objects are equilateral triangles. And basically, what are the things you can do to that triangle with features in the corners to leave it as the same triangle? You can rotate it, or you can horizontally flip it. This is all exactly the same triangle, just visualized from a different perspective, right? So these could be the symmetries of a triangle that we might want to be resistant to. And when you say a symmetry is a transformation that doesn't change the object, that immediately draws with it some mathematical properties. The identity must be a symmetry, right? That clearly doesn't change anything. If you have two symmetries, you can always compose them and get another symmetry. If you have a symmetry, you must be able to invert it, because if you don't invert it, you have dropped information, and therefore it hasn't preserved everything about your object, and so on and so forth. You collect all these facts together, you recover a standard mathematical object, the group. And this is just a collection of all those axioms, just written in a bit more abstract form. So a group is just a set G with all these transformations that you care about, and it must satisfy certain kinds of properties with its composition, right? Associativity, there must be an identity, there must exist an inverse, and so on, right? And this is, by the way, another really cool symmetry group, all the symmetries of a Rubik's Cube. You can already see as the objects get more complicated, so too the graphs of these possible symmetries do as well. And okay, so getting to the meat of things. So a symmetry group then contains all these transformations of omega to omega that hopefully leaves the omega unchanged. And you can then define a group action, which is an operation that applies this group element to a domain element and then gives you a transformed element or transformed data, okay? Such that some simple axioms are satisfied. And this is one example of such a group action. So if you have a Euclidean motion like rotations and translations, you can represent them using this kind of matrix, which you multiply with your features, and that rotates and translates the objects. And you can also then define what it means to have a data point on the surface, say, of a sphere, and then apply a group action to move it to a different point on the sphere. This is the equation that tells you how to look up the data function after you've applied the transformation G. This equation with G to the -1 just says, find me a point that will end up in use place when I apply G, and look up the function there. That's where it is. And it's also a linear thing usually, which means that it doesn't matter when you have a sum of two different inputs. It doesn't matter if you sum them first and then apply the action, or apply the actions and then sum them. You get the same outcome. And when you have this, you can define what's known as a real representation of a group action, this row of G, which is just a map that takes a group element and tells you a unique n by n matrix that computes that same thing. So in the case of graph neural nets, this was the permutation matrix. And this is another example of a cyclical shift matrix if you need to cyclically shift a one-dimensional input. I'm skipping quite quickly over some of these details just to get to the point that I want to make. And now that you have this, you can define the generalized notions of G invariance and G equivariance for any particular symmetry group, where you just replace what used to be a permutation matrix with the appropriate group action representation. And that's all. The ideas are the same. Invariance is if the output is unaffected by the action of the input, and equivariance is if the input and output are affected in the same way by the group action. I will skip these parts about orbits, so I can jump right into this general idea that using this concept, you can build all of the architectures that you care about by composing equivariant layers with then invariant layers at the end if you want to predict something over the whole domain. Why these equivariant layers can be linear? Because in deep learning, we usually just do a pointwise nonlinearity, and you can prove that that is sufficiently expressive. And sometimes you might want to do local pooling, although in graphs, we don't do that. Usually it hasn't been shown to be that effective yet. And together, all of these operations, stacking equivariant layers, maybe an invariant layer at the end, put some nonlinearity in between, local pooling, it's actually enough to rediscover all of the architectures that we have so far in deep learning. And in the book, we actually show how you can rederive all of these standard players by just choosing the right domain and the right kind of symmetry group. We've already seen in these lectures that you can rediscover GNNs, deep sets, and transformers as combinations of graph, set, or complete graph and the permutation group, right? And you can use the same idea to rediscover convnets, LSTMs, and even more exotic mesh-based CNNs. Now, I'm going to just skip over these parts. Some of these things should be clear, like permutation matrices are now just general group actions in the case of graphs. I'm going to skip over this so we can talk about specifically geometric graphs, which is something I promised to a few of you. So in general, so far, we assume the graph to be a discrete, unordered set of nodes and edges, but very often we might have some spatial geometry attached to this graph, right? So each node might have a 3D coordinate. This is very useful for any kind of physics or chemistry, right? And it was instrumental in the recent protein folding success of AlphaFold, for example. So in this case, you have some extra geometry attached to your nodes, and it might be very useful to exploit it beyond just permutations, right? So what's the general scenario we have here? Imagine you have features, so the usual features on your nodes, and also coordinates, which are, say, three-dimensional coordinates of where each node is in 3D space. Now, if you have a rotation or some other equivariant message passing layer, you transform them separately to get updated features and updated coordinates. And now you can express an additional symmetry group to be resistant to other than permutations. And one standard model in the case of molecules is the Euclidean group, E of 3, which covers rotations, translations, and reflections. So usually if you rotate the molecule, translate the molecule, or horizontally flip the molecule, it should still have the same molecular properties, ideally, right? This might not always be the case, like when it interacts with other molecules, but at least in isolation, this holds. So what this means is for any 3D orthogonal matrix R and translation vector V, I can define a group action that I want to be resistant to, which is multiplying by the matrix and translating by the vector. And if you apply to the coordinates, it should not affect the features, right? Because it's the same molecule, just in a different place. And there exist many possible ways to build a graph neural network that obeys this equivariance. Here, I'm giving you just one elegant solution that was proposed by Victor Garcia and others in this ICML paper, where you basically, you take this message passing mechanism that we had before on the features, but you don't put the coordinates directly into this message function, because then if you shift the coordinates or rotate the coordinates, you get a different output. What we do instead is we put the distance between the coordinates as an extra input to the message function. Why does this work? Well, if I rotate and translate my molecule, the distances stay the same. It's an isometry, right? So now this message passing equation totally respects the equivariance constraint. That's the main thing we did, right? We just added an extra input, which is the distance between the two nodes. That's it. And you need to have an equivalent equation if you want to update coordinates. I don't have time to go into details, but basically this computes a sort of weighted sum of all the kind of center of mass against all the other coordinates. And therefore, it's also resistant to rotations and translations. So you can convince yourselves, it's a nice algebraic exercise, that if I change my x's to be a rotated, translated variant of the x's, the f primes are the same, and the x primes will be rotated in exactly the same way, which is exactly the constraint that I want. Now, there is one problem with this class of models, and that is, what if some of your features also depend on the geometry, right? Like, what if you have to compute also forces between that act on each one of these guys? Now, the force is a vector in 3D space, so when you rotate everything, that force vector needs to rotate too, so you need to be careful about that. And the previous model wouldn't be able to take this into account. Here's a nice example. You have this scalar field, the heat map, with a vector field, the arrows on top of it. If I do a 90-degree rotation, the scalar field rotates accordingly and stays the same, but the force vectors rotate and change direction. So we have to be careful about this. And while in the original paper, Satoras and others do propose a modification of this layer that also updates the velocity features. So everything which is vector-based can also, we can invent a new rule for this. But, you know, you can see how this is an issue that will keep appearing as you tensor up. For every new, like a tensorial order, you need to invent a new equation that will update this. So you might ask yourself, can we talk about a general set of solutions that satisfy these equivariance constraints? I don't have a lot of time to go into the details, but the general idea is to use the theory of irreducible representations. So there are some group operations that can express all the other ones through combinations. And in the case of rotational symmetries, they turn out to be the spherical harmonics, which you can pre-compute. And then basically you have an equation of this tensor field network, which is basically, it feels like a graph neural network on the surface. The main difference is you multiply it with an extra matrix that you pre-compute, which is based on the geometric properties of the space. So and this can then also be extended to transformers. So this SE3 transformer paper is a really good read if you want to learn more about these kinds of things, because it kind of generalizes it to graph neural network ideas. And arbitrary order tensor, here you have L as the tensor order of your features. And it's, you know, computes query vectors, key vectors. So it's very familiar to those of you who have done transformers. But the general idea is you build a graph over all of your points in 3D space. You then pre-compute a bunch of mathematical things over those over that space. So the Clebsch-Gordon coefficients and spherical harmonics, all these things you can pre-compute. They're very tricky mathematically, but they can be pre-computed. And then they're just basically an extra matrix that you multiply with the standard message passing mechanism. So that's usually how this is executed. And a general point here is that you can then extend this idea to more manifold structured data, which is very useful for like computer graphics, protein design, fMRI processing. But if you look at how it's done, usually through this idea of parallel transporting a filter. So now imagine I want to convolve over a manifold, like this picture of Mona Lisa. On a simple 2D grid, this is easy to do. No matter what path I take from A to B, I'll get exactly the same filter. But if I now want to convolve over a mesh of Mona Lisa, if I decide to move this filter from the mouth to the right ear, it depends what's the path I take there. If I decide to go down the top of the head, I'll get a different oriented filter to when I go directly. So this is something we must be careful about when we build models like this. But even though it's a bit tricky, there have been very successful architectures that operate over the mesh structure. The geodesic CNNs and the gauge equivariant mesh CNNs are a really good example of this. But if you look at the equation of this mesh CNN, which carefully accounts for the geometry, this is the equation of the mesh CNN. You update the features of every node on the mesh of Mona Lisa by looking at some weight multiplied by the node itself, the input features, plus some sum over all the neighboring nodes, where you take the weight matrix multiplied by the neighbor's features. So this should feel a lot like a graph neural network, right? Over the nodes of the mesh. What's the main difference? This row guy here. This is a parallel transport matrix, which computes a change of basis as you go from point A to point B. But what's the key thing? This thing you pre-compute. Like upfront, based on the geometric structure of the mesh, you pre-compute a matrix and you insert it into a graph neural network rule. So you're still doing a graph neural network, only over a more complicated geometric object. And this addition of a matrix is mindful of the fact that you're dealing with a more complicated geometric object. And that's it. That's just a change of basis. And using these kinds of ideas, you can rediscover all sorts of different architectures. I just mentioned briefly mesh CNNs. If you want to see LSTMs, they're also in the book. So yeah, I think we are just about at time. So I will stop it there. Thank you very much. Happy to take more questions. Hope you enjoyed it.